Today, we're going to be discussing specific heat, specifically the specific heat of a metal or the specific heat capacity of a metal. This is a property of any compound that tells us how much energy it takes to raise the temperature of that substance. We're going to, typically this is found in joules per gram Kelvin, although sometimes you'll see it in joules per mole Kelvin, or calories per gram Celsius or something like that. But today we're going to actually measure it for an unknown metal. Now, first thing we always do when we get an unknown is look for any identifying features. And you can see there that one says SN. So we already know that SN is the identity of our metal. But so be sure to record that. But there's more stuff that we need. Whenever we're figuring out specific heat capacity, we're actually determining how much heat is transferred from the metal into water. We're going to do this using coffee cup calorimetry, or constant pressure calorimetry is the fancy term for it. Okay? In coffee cup calorimetry or constant pressure calorimetry, you have an amount of water, and we know what the specific heat of water is. You know the initial temperature of the water, you know the mass of the water, and you know the specific heat. Then you take a sample of your compound or your metal that you're going to determine the specific heat of. You're going to obtain its mass. We're going to specify what its initial temperature is. Then we're going to put the metal into our water in the coffee cup calorimeter. Now, remember the last law of the zeroth law of thermodynamics says that two objects that are in physical contact reach thermal equilibrium. That means love is communism, that you will wind up with everything having the same temperature if that system is allowed to equilibrate. Okay? So that's what we're going to do. We're going to have a hot piece of metal and some cool water, and we're going to let them reach the same temperature. That will allow us to determine how much heat was transferred into the water, which means that amount of heat had to have come from our piece of metal. Then since we know how much heat came from the metal, its mass, its initial and its final temperature, we can determine how much energy it took to change the specific heat of or how much energy it took to change the temperature of our metal, or that's called the specific heat. Okay? So for this lab, we're going to need a lot of equipment to get this set up, okay? So we're going to need two different ring stands. One of them is going to be running a Bunsen burner with just some tap water in it. We need a hot water bath. What we're going to do is take our sample of metal and put it into that water. Since that water is boiling water is always 100 degrees Celsius. So that means the highest temperature that our metal can reach is 100 degrees Celsius. So if we allow this water to come to a boil, and then we give that metal enough time, it will also be 100 degrees Celsius. We can use that as our initial temperature of the water. We're going to need a second ring stand though. And in this one, we're going to need the ring lowered down pretty far. We're going to put a 400 milliliter beaker into the ring. Then we're going to take 2 coffee cups, okay? Just 2 plain styrofoam cups. The reason we use 2 is that each of these is an insulator. That means that heat doesn't really transfer through it very well. That's also going to give us insulator air, which is an insulator, insulator air, which is an insulator, and then the glass. So we're not, essentially we're closing off, we're creating an isolated system or a closed system, depending on who you talk to. And then we'll put our 2 coffee cups right inside there. We're going to need a lid. Okay. We're going to need a thermometer and a thermometer clamp. So what we're going to do is adjust it so that the thermometer clamp, but the thermometer goes right through the center of that lid to the coffee cups. We're going to let the thermometer hit all the way at the bottom and then lift it up just a little bit so that it's not touching the bottom. Okay? And then we're going to clamp that in place. Now, there are some other things that we need to measure. So before I put this metal in here, I took it over to the balances and I weighed a 100 milliliter beaker, and then I put the metal in it and I weighed the metal in the beaker. The mass of the metal and the beaker minus the mass of the beaker is the mass of the metal, okay? I did the same thing with the coffee cups, but I did water instead of the metal. So I took my 2 coffee cups, obtained their mass, then added water, filled it up about 2/3 of the way with DI water, gotta be specific here, DI water, and then weighed it again. Okay? You'll be provided the mass of both the metal and the water.
Hey, we're back. My water back here is boiling, so we let it set for a good 10 to 15 minutes after it's boiling. Right? That means that the water is 100 degrees Celsius, and so is the metal inside it. Now, we have to move that metal into our coffee cup calorimeter. Now, problem here, we need the metal to not touch the thermometer. So what we're going to do is I'm going to take off just the lid, and I'm going to stick it up. I'm going to start by reading the initial temperature of the thermometer. So right now it's sitting at 23.0 even. Set this up so that I can see in here. I'm going to make sure that the ball of the thermometer is fully submerged, which it is, and I'm going to lower that just a smidge. So we're right in the middle there. And then, times, I'm going to put in my water and then close my coffee cup calorimeter. We're then going to allow the water and the metal to come to the same temperature, that thermal equilibrium that we talked about. The way we're going to know that happens is that the temperature of the water is going to go up and go down a little bit. The temperature that the water reaches is the temperature at thermal equilibrium. That will start losing some to the air that's in the container, to the holes that are in the styrofoam. So we're going to take the highest temperature that we see for that. So now let's do this very dangerous. We've got 100 degrees Celsius. So I'm going to knock off this water. To monitor this thermometer for 3 to 5 minutes, checking it every 20 seconds to see what that max temperature is going to be. Now, there is one other reaction that we could, measurement that we could take in a coffee cup calorimeter. That happens how the energy is exchanged for a reaction, say neutralization, that takes place in water. And the way we do this is incredibly similar to what we've done already, except instead of using a piece of metal and water that's already in the cup, we actually take 2 beakers, one that has a mass and one that has a base. We would measure their volume, we would measure the number of moles, we would figure out how many moles of the reaction is going to occur. And then we would figure out how much water is present, usually by volume, and then using density to find the mass of the water. When we pour those 2 solutions together, they're going to change temperature. So we're going to use the thermometer to measure the temperatures before we mix them. At room temperature, they should be the same temperature, so you really only need to measure one, but you always measure both, just to make sure. And once we've got those initial temperatures, we can pour them together, and we can follow and watch if the temperature goes up or down. If this is an endothermic reaction, that the temperature is going to go down for the water. And again, the lowest temperature is the temperature we want to be doing. It's an exothermic reaction, the temperature will go up, and the highest temperature is going to go down to the floor. That will allow us to know how much heat is exchanged in the water from the solutions. And then we can work backwards from that to determine the heat of that reaction, or even the enthalpy of that reaction.